Hello and welcome. I hope you are having a great day. In this video, we are going to discuss about Eigen Value Decomposition. So this is a very important concept in linear algebra, and this is the basis for principal component analysis, which is used widely, and singular value decomposition. So there are other two videos which will follow this after this. Okay, so let's set up the agenda first. So we'll discuss about eigenvalues, eigen vectors, diagonalization of a square matrix, and then eigenvalue decomposition, and after that we'll see a special case, that is spectral decomposition. Okay, so this is what we are going to cover. So let's begin with the first thing first. Why are we studying this? What's the meaning of eigen? We have been listening and learning this since our school days. So what does eigen mean? Okay, it's a odd word. So eigen, this word comes from Germany. So it's a German word which means proper or characteristic. So characteristic means some quality. Okay, so when you say characteristics of a person, so that's what characteristic mean. So eigenvalues means, or anything eigen means some characteristics, and we are talking this means all these. This is in the context of square matrix. So it's a continuous of matrix video that we did last. So this is about square matrix. Okay, and we know that a square matrix or a matrix, okay, any matrix in general, also a square matrix, so I'll just use matrix word, it transforms a vector. Okay, and this characteristic or eigen, okay, this talks about the some characteristics of this matrix. Okay, and what are those characteristics we'll discuss now. Okay, so let's understand first, do a quick revision, like how matrix transforms, does a linear transformation on a vector. So we'll continue the example. For example, so I'll just highlight this for your reference. We have a matrix A which is equal to 2 1 1 2, say. Okay, and we have a vector. So there is a vector u which is 0 1. So we say that this if we multiply this, so this matrix will linearly transform this vector, means it will change its direction and increase its magnitude. So it will change its direction or change its magnitude, or both. It can do either of them or both of them. So let's see what it does with this vector. So what's the product? So AB is equal to, so this is a, so remember matrix 2 by 2, this is 2 by 1. So these dimensions AB, these match, so these inner dimensions, they should match, and then we multiply, should come out as a 2 by 1. So that will be finally a vector. So that's why it's a vector. So what will be the vector? How do we do? So we multiply this 2 into 0 plus 1 into 1. So this is how we do. We go this row into this column. So 2 into 0 is 0, and plus 1 into 1. So this is your 1. And what is the other one? 1 into 0 is 0 plus 2 into 1, 2. So now after applying this transformation or multiplying this matrix, this 0 1 vector became 1 2. So let's see it on the for visualization. So everything linear algebra with equations is not so clear. So that's why we always go to geometry, and this we will keep doing throughout our machine learning or math learning, so that we can understand. So geometry is nothing but a visual representation of your equations, right? So this is the, and we are very visual, so that's why geometry is very important. Anything that we talk in terms of equations, even line or circle, everything, circle will have some equation, x square plus y square equal to r square. Okay, everything will have an equation, a parabola as y is equal to x square, but they are just formula and they are very dry, and when we see them, then we can put a name to this. Okay, this is an x square curve, like that. Okay, so that's the importance of coordinate geometry in short. So let's continue. So let's mark it 1 2 3 like this, and this dimension 1 2 3. This is 0, this is our x-axis, this is our y-axis. So what's the vector? So initially the vector was 0 1. So 0 1. So x-axis is 0, y-axis is 1. So it was here. This was a vector, unit vector on y-axis. Okay, after applying this matrix transformation, it became 1 2. So this is your 1, this is your 2, it came here. So after transformation, say it came here 1 2, let me put the point here, and this became here. So if you see the transformation, this vector which was 0 1 here, after being multiplied by this matrix, it is linearly transformed. So its direction changed from y-axis a bit, it shifted towards right, and also if you see the length has increased. Yeah, there are two things are happening. Okay, and let's see another example quickly. So this is what is happening. Okay, so let's see another example. Say for example, I have another vector called v. Okay, and this v vector is just 1 1. And now if I do a matrix multiplication of a into v, that is equal to 2 1 1 2 into 1 1, what will this be? So this will be 2 into 1 plus 1 into 1, so that will be 3, and 1 into 1 plus 2 into 1, so that will be 3. So this is your previous value, this was vector, and after applying this transformation or multiplying with the matrix, it became 3 by 3. So let's see what happened. So earlier this vector was 1 1, so my old vector is here 1 1. Okay, so let me make it, so this is 1 1, and after transforming it, it became 3 3. So it will continue the journey. So this is on the y equal to x equal to y line, so it will continue the journey, it will be somewhere here. So I'll just extend this line, it will be somewhere hitting the line here. So this will be my new vector, this long one. So this is your 3 3, earlier it was 1 1, here this is 1 comma 2, and this is your 0 comma 1. Okay, these are the coordinates. So if you see something with this vector, so this was this 1 1 vector, and for this vector it didn't change the direction, it was only its length increased. Okay, only its length increased. For this vector it changed its direction and length both. Okay, and for this vector it only changed its length, and this is what is called a Eigen Vector. So this is a characteristic of the matrix, in which direction it is giving me the change. Okay, this is the direction in which it is just scaling the vector, it is not changing the direction. So this is a characteristic of this matrix. If you have any vector in this region on this y equal to x, on this axis, if I treat this as an axis y equal to x, that will be like 45 degrees shifted here. If I have any vector, okay, 1 1 2 2 3 3 minus 1 minus 1 minus 2 minus 2, anything on this axis, if this is an axis, okay, all the vectors in this, you can, by the way, you can check it. Okay, all the vectors will just be scaled, they will be either the height will increase or decrease, mostly it will be increased. Okay, because of the eigenvalue, so it will be increased. And what is the, so this vector here 1 1 is called a Eigen Vector, or a characteristic of this matrix, because it, after multiplying with this matrix, this vector, okay, these kinds of all the vectors in this direction 1 1 2 2, all this will be different vectors, right? And this minus 1 minus 1 minus 2 minus 2, like that, all these are different vectors because the length is different. All of them will be scaled by 3 times, because this was scaled by 3 times. So this is, so the scaling factor is called eigenvalue. How many times this vector was scaled? So it was 1 1, that was one length 1 unit, that has become 3 3. So this has been scaled 3 times. So the scaling factor is called eigenvalue. So that is the characteristic, that by what magnitude is it scaling the vector, and what are the directions, vectors are directions, right? So what are the directions in which the vectors only scale, or the length changes, either it can increase or decrease, or it can like be reversed, right? Even the length can be it can go like minus 1 times, right? It can go on the other side also, so it can go that way. The size can be like, magnitude can be plus 3 or minus 3 also, right? So this vector will move in this direction, but the direction will remain same. And all these vectors on this axis line, these are called Eigen Vectors. This direction is generally sometimes called Eigen Basis also. Okay, so we'll talk about this when proper time comes, but for now, I hope you understand that the vectors which do not change their direction when multiplied by the matrix, those are the eigenvectors for that matrix. They only change their length, the scale is changed. Okay, and we know, right? So this 1 1 vector became 3 3 vector. So we can write it like 3 times 1 1 vector. This is a scaling factor, right? What is if I write c into vector v, then what is it? It will become cv1, cv2, all the entities will be multiplied. That's what it is. So that's why the basics are important. Okay, so that's what it did, 3 into 1 1, so it will just made a 3 3. So it scaled the vector by 3 times. So this is the scaling factor, a scalar unit. I hope now eigenvalue and eigenvectors are clear. What is an eigenvector? What is an eigenvalue? This is the characteristic of the matrix. This is only for this matrix, that in these directions, whatever vectors are there, they will just be scaled. Their direction won't change. And the scaling factor is called eigenvalue. And that will be characteristic for this matrix. And that's why this word comes. Eigen is like characteristic. Okay. I hope eigen is clear. So let's move and let's define our terms now. So what is an eigenvector? Whatever we discussed, I'll write it formally for you so that you remember. So what is an eigenvector? Here is a characteristic vector of a matrix. Okay, so I'll write it as special. It's a non-zero vector, because if you multiply by 0, then everything becomes 0. So it's a special non-zero vector or vectors of a matrix. It can be many. So I've just found one. So there can be many, and it will depend on the number of dimensions. We'll see this also when we understand the calculation, how many they can be. Okay, whose direction remains unchanged. Vectors of a matrix are vectors. I'll write matrix in it. Vectors whose direction do not change when multiplied by the matrix, or after transformation by matrix. Change after transformation or multiplication, right? Transformation is multiplication. Transformation by matrix is applied. I'm writing these words so that you can map it. When you hear like what is the transformation by matrix, it is nothing but just multiplication by a matrix, A into V. That's what we did. Okay, this is u. This is for u. This is for this one. This is for this one, and this V is for this one. Okay, so transformation by matrix is applied. So it might get scaled, but it won't rotate. Scaled means the length will change. So magnitude may change, it will not vary. It can be like magnitude can change once also, right? So magnitude may change, but direction will not change. So these are the characteristic vectors of the matrix. Okay, and the result is finally just a scaled version of the vector. So when we apply the final, so the result is result of a matrix A multiplied by vector V is equal to just a scalar multiple of vector V. Okay, and that's what we write it as lambda V. So lambda is the scalar, and we'll talk about lambda now. So I will talk about what is this lambda. This is the scaling factor. So your eigen value is the scaling factor of eigenvector. Okay, this is the base. You should understand this will, because if you understand this, then all of eigenvalue decomposition, principal component analysis, singular value decomposition, everything is same if you understand eigen. Okay, so scaling factor. So by how many times will the vector scale? Okay, So for example, if like mod of lambda is greater than 1, then it will stretch, right? It will stretch. If lambda, I'll just skip it. Okay, so the mod of lambda is between, like whatever lambda is, if it is between 1 and 0, then it will shrink. And if it is negative, then it will go. Lambda equal to 1 means unchanged, no change, means the same scale, right? So I'm just writing, and lambda is less than 0 means reverse the direction, reverse direction. So that's what it means. So the vector, whatever are the characteristic or eigenvectors, okay, and there will be the value, the characteristic value that will change, the eigenvalue, the way, the times it will scale is given by this eigenvalue, and from this you get the characteristic equation. Okay, that is kind of, so now the word has come back like characteristic equation. Earlier till here we have used eigen, okay, and eigen is like characteristic. You can just tell that also. So you can say now eigen equation or a characteristic equation. So what is the equation that will come out? Characteristic equation. This is a common term. I don't know why they keep switching between terms. So German back to English. So AV is equal to lambda times V. If I apply a transformation A on the vector V, it will scale. Lambda is a scalar. This is a scalar. Right at the bottom. This is a scalar. So the vector will just be multiplied by a scalar, as I showed you here. So this 1 vector became 3 so it's just like equal to 3 multiplied by this 1 vector. So all the entries will be multiplied by 3 like that. So that's what it means. Simple. Now let's solve this. So you will get the characteristic equation from here. So AV is equal to lambda V. So if I put all of them on the same side, this will become 0. So if I take the V part common, then we can write A minus lambda, but it is a matrix, so all should be matrix. So A and the dimension should match. So I'll create identity matrix of the same dimension, and this will become A minus lambda equal to 0. But I said, right, so this is a non-zero eigenvector, because if I multiply anything with 0, nothing is going to change. So if V is non-zero, like V is non-zero, right, and V is non-zero. So if V is non-zero, then it is having some direction. Okay, means this matrix. Okay, this matrix A minus lambda I will finally be a matrix only, right? Lambda times I'm doing a matrix of the same dimension. So this matrix should be singular. Singular means if it is a two-dimensional matrix, okay, if it's a two-dimensional matrix, then it is not changing the direction of the vector in two directions, right? If it's a two-dimensional matrix, then it should change it should rotate the vector also, because the changes will be on both the directions, on both the x and y axis, right? Since the changes are not happening in both the directions, means either of the directions has collapsed, means the matrix is singular. Okay, this resultant matrix is singular, that dimension has collapsed, the changes is happening only in the one direction. Okay, and that is called the dimension collapse. When we discussed matrix, I discussed about that. Okay, so this means that one of the dimensions has collapsed, and if it is 3D, 4D, ND, whatever, so there is a dimension collapse. Some dimension has collapsed, means the matrix is singular, and if the matrix is singular, means the determinant is 0, and that's why I was talking. So this must be singular. Then if this is non-vector, then non-zero vector. If lambda is non-zero, because that's what we started with, then this implies A minus lambda I, this vector, this matrix should be singular. That is, there is a dimension collapse. Around one dimension there is no change, so only there is a linear change in whatever direction it is happening. Otherwise it would move in some direction. The resultant direction of there is some force on x and y, right? So it will move in the resultant direction somewhere. But since there is only one direction, and what is the direction of that also we don't know. Okay, so that is the direct eigen basis of that. So but only one dimension is effective. So that's what I mean. So there is a dimension collapse, and that's why the vector is changing only in one direction, and the vector is the matrix is singular. And for singularity or singular matrix, we have Determinant of A minus lambda is equal to 0, and this is your characteristic equation. Say for example, if we have a vector A is equal to, let me make a bigger vector. I'll give you a general form: A11, A12, like this till A1n, and we have ANN. Okay, A21, A22, like this. Okay, so your A minus lambda I will be, so I is a identity matrix where 1 1 1 is there and 0 0 0 everywhere. Only the diagonal has 0. Say if this is 3 by 3. Okay, if it is this one, only I is identity, right? So only the diagonal has 1. So if lambda is multiplied by I, means only the diagonal elements will be multiplied, rest everything is 0, nothing is happening. So if I subtract A minus lambda I, means only the diagonal elements will get subtracted, because nothing is there on these that apart from the diagonal. So the diagonal elements will change. A11 minus lambda, okay, and then A22 minus lambda, like this till ANN minus lambda, and here it is like A1n, AN1, A12, A21, like that. Okay, this is the matrix. So A minus lambda is this, and then determinant of A will give me. So this is a say for example, this is a n cross n matrix. Okay, this is n cross. I'm talking about square matrices. Okay, that's the assumption on which we are moving now. Okay, square matrices only. So this is a n cross n matrix, means this will be determinant. Finally we will have how many lambda terms? N times lambda will be figuring here. So finally if we create take a determinant of this, so lambda will be multiplied by how many times? If I keep on going, n times. So this will give rise to a polynomial of degree n. So this will give me a polynomial. This will give me a equation, polynomial equation in degree n, because n is the dimension for lambda, and we'll solve that to get the equation, right? And we'll solve the equation to get all the values of lambda. Let's do an example that will make it clear. I'll keep continuing the same example. So this is my example, right? So yeah, the matrix will be A21, 1 2. Okay, I'll take this only and keep on building on this. So let's do this example. So for example, let's do for this only. My matrix is A is equal to 2 1 1 2. So A minus lambda I will be equal to 2 minus lambda 1 1 2 minus lambda. So what will be my determinant of A minus lambda I is equal to this should be 0. This implies, so what is the determinant? AD minus BC. This implies 2 minus lambda into 2 minus lambda, that whole square is equal to 1. This implies taking a square root, 2 minus lambda, I can write it other way around. Lambda minus 2 whole square is also same thing, right? And I can write, I have taken a square root, and then finally I can write plus minus 1. This implies lambda can be equal to 2 plus 1, lambda 1, or lambda 2 can be equal to 2 minus 1. This implies lambda 1 is equal to 3 and lambda 2 is equal to 1. Okay, so this 2 goes this side and there's a plus 1. So 2 plus minus 1. So 2 plus 1 is 3 and 2 minus 1 is 1. So these are the two values of lambda. Okay, so these are the two values of lambda we got. So let's put this in the equation and find out the corresponding lambda eigenvectors. So these are my eigenvalues. These are my eigenvalues, scaling factor. On one direction it is scaling by 3, and on the other direction it is scaling by just 1 time. So this is the scaling factor also. So let's see. So we have A minus so now let's find out the eigenvectors, corresponding eigenvectors. So when we just put the values back, right? So we know that A minus lambda I, what was the equation? V into so this is the V into A minus lambda I equal to 0, right? So V is, say, 2 dimensions here, because there are 2 dimensions. V is V1 V2. So a minus lambda is 2 minus, say, for lambda 1 equal to 3. Okay, 2 minus lambda 1, 1, 2 minus lambda, this is the lambda, and then this is your v1, v2. Okay, equal to 0. This implies, so 2 minus lambda, lambda is, what is lambda? Lambda is 3. So 2 minus 3, 1, 1, 2 minus 3, v1, v2 is equal to 0, like that. And then this will be implies 2 minus 3 is minus 1, 1, 1, minus 1 into v1, v2 equal to 0. So what will be my eigenvectors here? So this is the equation. So multiply this. So we'll get two equations in V. So this is minus v1 plus v2. This is minus v1 plus v2 equal to 0. So this 0 is like 0, 0, like this. Okay. And then the other equation is also like that. v1 minus v2 equal to 0. So this just implies v1 is equal to v2. So as I mentioned, so v1 is equal to v2 means x is equal to y. So these are the dimensions on x and y. These are two dimensions. So any vector on this dimension x equal to y. Okay, sorry. Any vector on this axis x equal to y will be a eigenvector. We'll take the smallest one. So we'll say we can take anyone. So we'll take v1 equal to v2 equal to 1. So my eigenvector will be, so v is equal to 1, 1. So this is your v or v1, sorry, corresponding to lambda 1 equal to 3. Similarly, lambda 2 is equal to 1. So I'll directly 2 minus 1, 1, 1, 2 minus 1 into v1, v2. So this is for the second vector. So I have just written v corresponding to lambda, but again, so these are the two components of vector, like on the x-axis, on the y-axis. So we write v1, v2, v3 till n dimensions. So this is equal to 0, 0 because it is 0. So just equating. This implies 1, 1, 1, 1, v1, v2 equal to 0, 0. So I'll just skip the 0. So it is simple. v1 plus v2 equal to 0. Both the equations will be same. This implies v1 is equal to minus v2. So what does this mean? So anything on the x equal to minus y or y equal to minus x axis. So where it will be. So I can take the smallest one. So here my v2 corresponding to lambda 2 is equal to 1 will be 1, and I can take minus 1. So these are my two vectors. So this is v2, and for v1 this was lambda 1 equal to 2. I had v1, this was 1, 1. So this is how we compute our eigenvalues and eigenvectors. So this is my this is 3. So for lambda lambda equal to 1, I got this vector, and for lambda equal to 3, I got this vector. I hope this calculation is clear, right? So this is how we calculate eigenvalues and eigenvectors. So these are the characteristics of this matrix only. Okay, this one won't be, sorry, yes, something I touched. Okay, so let's continue. So I have a question for you now. So if this is clear, okay, all this calculation, you can do, the math is simple. If this is clear, right, let me ask you a question. So what are the eigenvalues and vectors of an identity matrix? So if I have to find eigenvalues and vectors of identity matrix, what are these? So this will be a minus lambda I, determinant of this will be equal to 0, right? Here this is I minus lambda I equal to 0. So if we solve this equation, what will be? What it will be? 1 minus lambda, 1 minus lambda, 1 minus lambda, like this, 0, 0, 0, 0, everywhere. If I take n dimensions, whatever is the dimension here, this means if I, and this finally, all the everything is 0, so finally this will be equation like 1 minus lambda, 1 minus lambda, 1 minus lambda, whatever n times, this will be equal to 0. This just implies that lambda is equal to 1, and this also shows that the diagonal elements. Okay, if a matrix is a diagonal matrix, the lambda values will be the diagonal elements. So if I equate this simply, so earlier without this equation, right, what is identity matrix? Identity matrix will be like 1 1 1 1 0 0 0 0 0 0, like that. All the diagonals are 1. So I can say these are the if. So there's another thing also, you can verify that. We know for a fact that if a square matrix is a diagonal matrix, then the values on the diagonal are its eigenvalues. So for this, the eigenvalues are 1 1 1, and any vector will satisfy this equation. Okay, if you solve this, any vector will satisfy this equation. You can just put the values and see. Okay, I'll leave this as an exercise. Similarly for diagonal matrix also, the values will be this. So now I'll give you some properties of eigenvalues and vectors, which we know already, but I'll just write it down for you. So I'll just reiterate. So what are the properties of eigenvalues and eigenvectors? Some good to know stuff. Okay, so if your square matrix is, again we know, if your square matrix A belongs to n cross n, that is, it is a n cross n matrix, it's an n cross n square matrix, then you will have n eigenvalues. Some of them, they may all be equal, they may be different, some of them may be 0, but there will be n eigenvalues. And for each one, each characteristic, we have a different behavior, but there will be n eigenvalues, because we know from the polynomial, right, that polynomial quotient in degree n, because of this, and this will give me n solutions. This will give me n solutions for lambda, because this is degree n polynomial. Okay, in one variable. Similarly, if x equal to something, x square equal to something, give me plus minus 1, x cube equal to 1, then it will give me 3 values, like that. You can just keep on increasing the power, and that many values you will get. Okay, so this is the first one. What else we have? So they may not be distinct, as I mentioned already. Okay, and there are two good things to know. So one, the sum of eigenvalues is equal to trace of the matrix, and then product of eigenvalues is equal to determinant of the matrix. You can check that quickly here. So for our case, okay, for example, our case, A was equal to 2 1 1 2. What were the eigenvalues? Lambda 1 was 3, lambda 2 was 1. Okay, what is the trace of matrix A? Is equal to 2 plus 2, 4. This is equal to, is it not equal to lambda 1 plus lambda 2? There is a proof also for this, but we'll skip that. And similarly, determinant of A is equal to 2 into 2 minus 1 into 1. This is 3. Isn't it equal to lambda 1 into lambda 2? That equals 3 into 1. This is your 3 plus 1. So just a quick proof, verification of what we have seen already. Sorry. So these are some, okay, properties. Okay, one important property. So the trace of a trace is equal to sum of eigenvalues, and the determinant of the matrix is equal to the product of the eigenvalues. So you can, these are also used at many times for fast compute. Okay, so there is one important property where if the eigenvalues are distinct, then corresponding eigenvectors will be perpendicular to each other. Corresponding eigenvectors will be perpendicular or orthogonal to each other. I'll prove you this if you want. We can prove this. Okay, let me prove it so that you will know. So even in this case, you can see, right? So what were the eigenvectors we got? These are the eigenvectors. Let's plot them. I don't know if this is visible. Okay, so these are the vectors. So we have, so first vector is 1 minus 1. So this is just, say for example, this is your 1, this is 1 minus 1, 2, 2, like that. Okay, so the first vector is 1 and minus 1. So this is your 1 here, this is 0, 1, 2, minus 1, minus 2, 1, 2, like that. So the first vector is here 1 and minus 1. So this is your first vector, like this. And the second vector is 1, 1. So this is your 1, 1 is here. So you see, this is a 90 degree. Here we can see, because 1 was corresponding to lambda is equal to 1 and lambda is equal to 3. This is lambda is equal to 1. This is ulta. This is lambda is equal to 3 and this is lambda is equal to 1. So you see, this is 90 degree. Okay, this you have seen also here. Okay, this is, so similarly you can prove that also. So let me quickly prove it for you. Okay, so so we know that first of all that scaling a1 av1 is equal to lambda 1 v1 and av2 is equal to lambda 2 times v2. So this is your first thing we know for a fact. Now let's find out that what is the dot product of the scaled vector av1 dot v2. Okay, let's find this out. So this we can write as, what is a dot product of u dot v is equal to u transpose v, right? We'll take this. So av1, and also we know ab whole transpose, okay, I don't know, I'll bring it here, is equal to a transpose b transpose. So these are the things which we know already from the past. Okay, so we'll write it. So av1 dot, this is a dot product, so this will be av1 whole transpose into v2. Okay. So what is, okay, so let me bring it here. So this is there, so this will be equal to, what is av1 transpose? This will be v1 transpose a transpose v2. Can we write it as a transpose equal to a? Okay, because, okay, for a symmetric matrix, okay, I didn't, okay, so for a symmetric matrix also, that condition I forgot, vectors will be, it's either for, okay, this is a, for a symmetric matrix. So this is a condition, that is A is equal to A transpose. So for a symmetric matrix, the distinct eigen values, okay, for them the corresponding eigen values will be orthogonal. So if A, then A transpose is equal to A. So now if I see this part, A transpose V2, okay, so first of all let me replace this with V1 transpose and A transpose A V2. What is this? A transpose A V2. Can we write it as lambda 2 V2? This is the scaled version. If I apply A, then that will scale it. So this is equal to V1 transpose lambda 2 V2, and this is AV1 dot V2. This is what we are calculating. And what is AV1? AV1 is lambda 1 V1. So this is a lambda 1 V1 dot V2 is equal to V1 transpose. So again, this is U transpose V. So one vector transpose other vector. So this multiplication, can I write V transpose V dot lambda V2, V1 dot product. Here also there is a dot product. Here also there is a dot product. This V1 transpose into this was there. So I just converted this into this. And now let's bring all of them together. So this lambda is just a scaling factor, that's a number. So I can write lambda 1 into V1 dot V2 minus lambda 2 into V1 dot V2 is equal to 0. This implies lambda 1 minus lambda 2 into v1 dot v2 equal to 0. But we know that lambda 1 is not equal to lambda 2, because that was the assumption that if both are distinct and it's a symmetric matrix. Okay, so if this is not equal to 0, then this should be 0. This implies v1 dot v2 equal to 0. This implies v1 perpendicular v2, or v1 and v2 are orthogonal to each other. So this is a quick proof. Okay, important thing. So if we have a symmetric matrix, then for distinct eigenvalues we can assume that vectors will be perpendicular and orthogonal. And we also know for orthogonal, what is orthogonal? If two vectors are orthogonal, they are also linearly independent. We saw that in the orthogonal when we are talking orthogonality of matrix. Okay, so if two vectors are linearly independent, then they may not be orthogonal. But if they are orthogonal, then this is the extreme version of independence, that okay, there is no influence of one vector on the other. They are 90 degrees apart in the coordinate system. So that's the extreme case of linear independence. Okay, because I cannot represent the other vector in the form of this vector in any way. So they are linearly independent. The two axes or coordinate axes are always linearly independent. And that is clear. Okay, so that's why this is very, very important. Orthogonal vectors are linearly independent. Remember this. Okay, so if this is clear, this is eigenvectors. So eigen is clear now. Okay, now let's move to the next concept, which is the precursor for eigenvalue decomposition. Okay, what do we mean now? So everything around eigen is clear, that these are the characteristics of a matrix, where eigenvectors are those directions or those vectors in which if I apply the matrix, then only the vectors will scale. There will be no change in direction, and the change in the length of that vector either increase, decrease, that is your eigenvalue. Okay, these are the characteristics of this matrix. This is clear. Let's move to the next concept. Okay, before that I'll ask you a question. Okay, so we'll understand this. Okay, so how will you calculate the power of a matrix? Say for example, if I have a matrix A, okay, and I want to calculate A square, how will we calculate it? We'll multiply A into A, right? Okay, what if I want to calculate A to the power K? How many times will you multiply this matrix? Multiplying, okay, you will say that 2 times is easy, but how many times will you keep on multiplying this? So this becomes cumbersome. Okay, for example, if we have to calculate for our simple matrix, I'll give you example. Okay, for example, our same matrix. Okay, A is equal to 2 1 1 2, then your A square will be 2 1 1 2. I'll do a fast calculation. 2 1 1 2, so this will be equal to 2 into 2 4 plus 2 into 2 4 plus 1 into 1 1, so that will be 5. Okay, 2 into 1 1 plus 1 into 2 2, so that will be 4. Again this will be 4 and this will be 5. 1 into 2 plus 2 into 1 4, and then this will be 1 into 1 plus 2 into 2, so 4 5. Okay, so this is way. Now if I keep on telling that I want e to the power k, so how many times will you multiply? This becomes difficult. So that's why, so there's another question now. Say for example, question 1. Okay, for example, if I have a matrix of this form, so my A was like this, right? So if I have a matrix of form like this 2 0 0 3, what will be A square equal to? This will be equal to A into A. So let's multiply and see. 2 0 0 3. So if you see, you can pull everything a bit right. Okay, and this also a bit right. And let me bring it down so that I don't. So A square is equal to this, and this will be equal to, what will be the value? 2 into 2 plus 0 into 0, so that will be equal to 4. This one, 2 into 0 plus 0 into 3, 0, 0 into 2 plus 3 into 0, 0, and this one 0 into 0 plus 3 into 3. So this will be 9. Do you see this is nothing but 2 square and 3 square and rest is 0. Similarly, if I have a to the power k, you keep on doing this, you can try that, then you will get something like, if the matrix is diagonal, a diagonal matrix, okay, and rest all the elements are 0, then a to the power k will be nothing but your, it's a diagonal, a11 to the power k, a2 to the power k, ann power k, and rest everything is anyway 0, 0, 0, 0. So don't you think our power calculation will become very easy this way? And we are in mathematics many places, okay, you will calculate powers and matrix is there and you have to calculate this, even e to the power a, these kind of things you have to calculate, okay. So these will become very cumbersome if I go with the conventional way of multiplying, okay. And for solving this, we saw that if we have a diagonal matrix, it is becoming very easy. I have to just, I know all these entries, these are scalars, and I can increase them to the required power, whatever is the power, and this makes it very convenient or fast. That's why it is important to learn, like, how can we diagonalize any matrix, how can we diagonalize, and that's the one of the important use cases. The other use cases also, this is an example to just show you, but there are many applications that if we diagonalize the matrix, then our mathematical operations become very easy. So let's understand how to diagonalize a matrix. So how to diagonalize now? If there is any square matrix, how can we diagonalize it? Okay, how to diagonalize a square matrix? Because we are in the context of square matrix. Everything is under square matrix. That's the question. How do we diagonalize it? So I'll tell you the steps. Okay. So the steps will be. So first of all, okay. So there's a condition. Okay. There's a condition. We can only diagonalize a square matrix if, okay, it is diagonalizable if and only if, the I with double F, okay, if and only if, that is IFF, if the square matrix has n linearly independent eigenvectors. Okay, if and only if it has n total, if the square matrix is of dimension n, right? So given that my A is n cross n, so if my dimensions of the square matrix is n cross n, then my vectors, all the eigenvectors I should have, after solving the equation for this determinant, and I'll find all my eigenvectors. So finally I should have n linearly independent eigenvectors. If it is any less, then I cannot diagonalize a square matrix. So this is the important thing to know. And we also know that we have seen now that if it is a symmetric matrix, right? If it's a symmetric matrix, then for all the distinct values I will get orthogonal matrix, orthogonal eigenvectors which are linearly independent. So we also know that. So we'll keep that in mind and we will revisit that concept again. If you have distinct, if the matrix is let me rub this off. So note it. If your square matrix is symmetric, that is A equal to A transpose, that is symmetric, then for all distinct eigenvalues implies perpendicular eigenvectors. They are all orthogonal to each other. This means they are linearly independent by default. Linearly independent. Okay, you know this. So we keep this in mind and we'll revisit this concept. So now how to make this, how to formulate this. So there are steps. Okay. So first of all, so we know that, now let's come back. We know that A is equal to lambda v. So this is our eigenvalue equation. Okay. So what if now I have, okay, I have a set of, I have found for n dimensions, okay, for n dimensions, I'll get my n eigenvalues, assuming all of them are non-zero and distinct eigenvalues. So that's the assumption. Let's start with that. N eigenvalues that are distinct, and if they are distinct, corresponding to them, I have n distinct eigenvectors. So I have n eigenvectors. Okay. So if I put them all together, okay, so I have this matrix and I have n eigenvectors and I have n eigenvalues corresponding to them. So can I generalize everything and write it into one big equation? So can I write this small v as a capital V? A V is equal to capital lambda V. So this V, what am I saying? What is this V? So this capital V is nothing but I have combined all my eigenvectors together in one vector and I have put them in as columns here. So I've combined all this is my eigenvector 1, V, eigenvector 2, eigenvector 3. So these are my eigenvectors. So I've combined all my eigenvectors together. So these are my eigenvectors. Okay. So all these entries will be here, n dimension. This is n cross n. Okay. So I've combined all this together. So this is giving me the capital V. Okay. And what is this lambda? This capital lambda. This is a capital lambda. Okay. So just don't confuse. This is capital lambda. Capital lambda. So this is putting all my lambda values together. Sorry, eigenvalues together. So this is lambda 1, lambda 2, like this on the diagonal, and lambda n, and rest everything is 0, 0, 0. So I put them on the diagonal, and this V is same. This V is both the side because AV was lambda V. This was our characteristic equation of that this matrix is scaling my eigenvector by lambda times. And now all the eigenvectors for this n dimensions, I have put them in one matrix as columns, and I put them together now and have generalized it that A times, okay, so if we write, so for example A times V, how do we see this? So this will be like A times, so AV will look like, say, A times my V vector is the small v's are there, right? V1, V2 like this till Vn. So this will be nothing but a combination of AV1, AV2 like this, AVn, right? Similarly, this capital lambda and V will be equal to nothing but lambda I have put like this, lambda 1, lambda 2 like this till lambda n, rest everything is 0, and into these vectors V1, V2, Vn, these are my eigenvectors here. Okay, and finally what will be this form? Like this will look like lambda 1 V1, lambda 2 V2, and lambda n Vn. Okay, so I'll just squeeze it this side. Let this be. Okay, so I'll rewrite this here. I'll bring only this part here. So will this not look like this? I'll write it more cleanly maybe. So this is like a lambda 1 V1, lambda 2 V2, lambda n Vn, like this. So if you see the equation, all the equation in one context, right? So this is nothing but AV1, AV2, all of them are put together, and this is your lambda 1 V1, lambda 2 V2. So all the vectors are multiplied by A, and all the vectors have eigenvectors they are being scaled by lambda. So I put this in one equation, and this is how we are putting it together. Okay, and that is what is this vector AV is equal to lambda V. And if we can write like this, if we can write any vector in this format, so my vector is looking like A capital V is equal to capital lambda and V. Okay, all this V are the columns of V are my eigenvectors. Columns of V are my eigenvectors. And we saw that how am I visualizing this? AV1 is like multiplying A with all the column vectors. So all these columns like this, I get AV1, AV2, and lambda is a diagonal, and then lambda 1 into V1, how much this is scaled, lambda 2 into V2, how much V2 is scaled, lambda n into Vn, how Vn is scaled. Rest everything will remain 0 and they will not impact other vectors. Okay, so this is how we are representing. So this is the same thing we have written for all the vectors combined. And now if you look at this equation, okay, now if you look at this equation, can I write, if I bring this v this side, so this implies v inverse a into v is equal to lambda, and what is the lambda? Lambda, you are seeing this is a diagonal matrix. This is a diagonal matrix. We have put them because it is not impacting other dimensions, only the dimensions in which it is applied. Okay, so this is your diagonal matrix. And now do you see, by just multiplying this A vector with its all the collection of eigenvectors and the collection of it, the inverse of eigenvectors, I have converted it into a diagonal vector, into a diagonal matrix. This is a diagonal matrix. So don't you think this A is converted to a diagonal matrix now? So isn't it diagonalized? So this is nothing but your diagonalization of a matrix. So if you multiply a matrix A with its vector and with its combined all the eigenvectors and its inverse, then finally you will get a diagonal matrix. So this is how you diagonalize a matrix. So this is your diagonalization. This is called diagonal matrix. I hope this is clear, because lambda is a diagonal matrix, right? If this is clear, so just a step ahead, if you just rehash this, then you will get, I'm just rehashing the same equation. Can I write A, if I move all the v to this side, if I move this v and this v to this side, can I write A as v lambda v inverse? Can I write it like this? Can A be represented as like this? Okay, so this is your diagonalization, and this is what is called your Eigen Value Decomposition. This is your Eigen Value Decomposition. We have decomposed this matrix or reconstructed this matrix into a vector v which has all the eigenvectors, vector lambda whose diagonal entries are all the all your lambda eigenvalues, and this is the v inverse of the same matrix which has all your eigenvectors. So this is your Eigen Value Decomposition. And what is lambda? Lambda is giving the scaling factor in each direction, right? So vectors are in which direction I am scaling, okay, and this is giving by how much I am scaling. So this is just taking that I am taking a matrix A, rotating it along the eigenvector direction, scaling it in that direction, and then rotating it back. Okay, so I'm just taking it in eigenvector direction, whatever is the eigenvector. We had like this, we saw 1 1, right? So this was the eigenvector direction. So I rotate my matrix in eigenvector direction, scale it by lambda times, and then again take inverse, so it will rotate it back to this direction. So finally I'm getting the same matrix back if I do all these operations. But at the end, okay, so I can represent, so this v and v inverse are fixed. So this lambda here is your diagonal matrix, and this gives it a beautiful, this lambda which is a diagonal matrix, this gives it a beautiful property. Now if I have to calculate the diagonalized matrix, right, now if I have to calculate a to the power k, I just need to know whatever was there, I just need to compute its v, that was your vectors, all the eigenvectors, put it all the eigenvectors and put them in a matrix. Then lambda v inverse, I just need to raise this lambda to the power k, and since lambda is a diagonal matrix, what did we say? That only these will be raised to the power k, and then these all, and we just multiply them. These all are fixed. These are eigenvectors, fixed eigenvectors. And if I have to, even if I have to take now any power of a, this will be calculated once, and just vary this lambda to the power k, and I can compute multiple powers, a square, a cube, a and whatever power, just by changing this lambda. And these are some scalars whose powers will change, and this is what makes it so powerful and so useful. mathematically and computationally, right? This makes our life so easy. Only the lambda will change. Sorry, this lambda to the power k will happen. And even if I have like e to the power ak, okay, so if I have vector, if I want to do exponential of this e to the power a, this a is a matrix, okay, a is a square matrix, so this will become v lambda, okay, to the power e, okay, this will be e to the power a, e to the power a, v inverse, like this. So all the diagonal entries of this lambda, they will be, so if you do this, right, so there will be e to the power lambda, it will become like that, okay, this will become e to the power, so let me write it in a different way, it will be e to the power lambda, because a will be becoming lambda here, so e to the power a, so all my diagonal entries, this will become, instead of lambda, it will become e to the power lambda, e to the power lambda 2, e to the power lambda, like this. So you see, this will become, so instead of calculating this, right, this will be so cumbersome. This is the mathematical hack that will make our life easy, and that's why diagonalization is important, and that's why Eigen Value Decomposition for mathematics is important. There's one more very important application, that is PCA, which is we'll discuss in the next video. Okay, so I hope Eigen Value Decomposition is clear and why it is important. Okay, if this is clear, let's do one more small thing after this. Okay, so you can verify it also. You can just put all the values. For example, if you know how to calculate inverse, right? So for example, for this vector, a was 2 1 1 2. I leave the maths for you, and we calculated v. So v1 was 1 1, and our v2 was 1 minus 1, like that. For v11 was corresponding to lambda equal to 3, and this is for lambda is equal to 1. So now if I can put a as v lambda v inverse, so my v is, I'll put both the eigenvectors together, v1 and v2 here, 1 and minus 1 into lambda. So one eigenvector is 3, one is 0, and then inverse of this 1 1 1 minus 1 inverse. So compute the inverse of this. So inverse of this matrix only, right? It says this is the inverse of this. So you know, this is a simple calculation. You can calculate the inverse of this, and then these are the values. If you calculate this, finally you should get the matrix back. You should get 2 1 1 2. Okay, so just try doing this and you should get it back. This is simple matrix multiplication, and that will prove that yeah, this works and I get the same matrix back. I hope that is clear. Okay, so inverse and everything we know how to calculate. That is in the other video. If not, I'll put those links in the description. Okay, and we'll just understand one more thing, which is, say for example, now these vectors that we have got, okay, these vectors that we have got, we know they are coming from distinct, these vectors, eigenvectors, are coming from distinct eigenvalues, so they are orthogonal to each other. Okay, but are these vectors orthogonal? So orthogonal vectors have a very beautiful, orthogonal matrix has a very beautiful property, right? So if is v, so if this is v, right, so this v is equal to 1 1 1 minus 1, is it orthogonal? These vectors are orthogonal to each other. We have proved that for a symmetric matrix, because this is a symmetric matrix, right? 2 2 1 1. So this is symmetric matrix. A is equal to A transpose. For distinct eigenvalues, I'll get orthogonal vectors, orthogonal eigenvectors. So these are orthogonal to each other. We have seen that in the diagram also, that one is here, 90 degrees there. But is it an orthogonal matrix? Not yet. So what was the condition for orthogonal matrix? That all the vectors, say for example, if this is v1, this is v2, so v1 should be perpendicular to v2 or orthogonal, means v1. So this first condition is v1 dot v2 should be equal to 0 because they are perpendicular or orthogonal to each other. And second was each vector should be a unit vector, and that made it normalized by the by divided by the length, so this become unit length. So this second condition is not satisfied. If you see the length of these vectors, what is the length of these vectors? So what is the length of this vector? Which is 1 1 square root of 1 square plus 1 square, that is square root of 2. So these are not unit length, right? These vectors, both of them are not unit length. So we need, for this vector to become orthogonal, we need them to be orthonormal, and for orthonormal we will have to divide them with their each vector by their length. Okay, and after that, what the vector which we get, this vector v will become a orthogonal, the matrix that we get after converting each one to orthonormal, it will become a, and then this finally it will become a orthogonal matrix, because both the conditions are satisfied. Currently only one condition is satisfied. So, and what is a beautiful property about orthogonal matrix? That Q transpose is equal to A transpose is equal to A inverse for orthogonal matrix, because A transpose equal to A transpose A equal to I. So this is a very beautiful property. From there we derive that this is a beautiful property of A transpose. And why am I telling you this A transpose? Because calculating transpose is easier than inverse. That's why we are moving from inverse to transpose. Transpose is just flip rows and columns. Inverse is like a cumbersome problem, and also inverse we may not be able to calculate if the determinant is 0. So that's why we are moving to this transpose form. Okay, that's the reason. So here we have A is equal to V lambda V inverse. Somehow if I make this V transpose, and currently I have all the ingredients, it's orthogonal, the vectors are orthogonal to each other, but this matrix is not orthogonal. And if we just divide it by all the vectors by their length, then finally it will become orthogonal, because all the vectors here will be unit length. So how do we do this? How do we write it? Okay, so if we take orthogonal eigenvectors and then we normalize them. So if we normalize, that is divide by length of vector. Okay, if we normalize each eigenvector, then they will, so by their length, so this will be like vi equal to 1 for making this. So finally the normalized, if I say normalized eigenvector, that is v divided by length, vi divided by its length, if I say this qi, and now if I put all this qi's into one vector, if I put them into q1, q2 like this till qn, which are all normalized v. Okay, so this is just note it here. So they are divided by the length of them. If I put them there now, so now this q will become a orthogonal matrix, because both the conditions are satisfied. They are q1 dot q2 equal to 0 and q1's length is equal to 1. In general form, qi dot qj is equal to 0 when I not equal to j, and qi dot qi, okay, let me write qi dot qi equal to 1, that is I equal to j, right? I equal to j, same thing. If we generalize it, so I can write qi dot qj equal to 1 if I equal to j and equal to 0 if I not equal to j. Okay, if I do this now, so this v after my v vector after normalization has become q. So can I write the same vector a? A was equal to v lambda v inverse. Can I write now A is as q lambda q transpose? This q is nothing but normalized v. My q is nothing but a normalized v. I'm dividing each vector by its length. So now I have got the same form. Okay, same thing in the transpose format. This inverse format is your eigenvalue decomposition. This is your EVD, and this is called, it has got a special name because this is called a spectral decomposition. And remember everything because all these are orthogonal, we have assumed, right? So this is for any square, this is just for square matrix, but here this is for symmetric, because only then, right, for symmetric matrix A is equal to A transpose, only then for all the distinct eigenvalues I'll get orthogonal eigen vectors. I hope this is clear, the difference, why this is preferred, because transpose is easy. So if I have a symmetric matrix, which is mostly the case in the world of machine learning, because mostly we'll be dealing with variance and covariance, and covariance of xy is equal to covariance of yx, so such kind of cases. So both will be same, and the matrix finally what will come out will be a symmetric matrix. So we'll be dealing mostly with symmetric matrix. That's why you will see this format. This is only for square matrices and this is for symmetric matrices. And plus we have normalized the length of all the vectors which were orthogonal to begin with. I hope this is clear. If orthogonal etc is not clear, we have proved that also. Okay, check the matrix video. I'll put the link in the description. Okay, so you can quickly check all these also. Okay, so this A is equal to Q lambda Q transpose, you can do the maths and check it. So that will give you more confidence that how everything is coming, as I told you right here. This calculation. Similarly, after normalization, right, we found out what will be Q. So let me quickly show you. So if my V is equal to 1 1 1 minus 1, right, so this vector's length I'll divide by root 2, and this also I'll divide by root 2 because both of them are root 2. Okay, so I can write it as 1 by root 2 1 by root 2 1 by root 2 minus 1 by root 2. You see 1 by root 2 is common everywhere, so I'll just remove this. So my Q will become 1 by root 2 normalized form, 1 1 1 minus 1, and the Q transpose will be 1 by root 2, same thing. Now I don't need to calculate the inverse. So 1, so rows will become columns. Okay, and then 1 minus 1, same thing, it will become the same thing. I'll put 1 1 here and then 1 minus 1 here. Okay, so it will become the same thing. So now my A will become Q, that is 1 by root 2 times 1 1 1 minus 1. Lambda remains same, 3 0 3 1 0 0, and the next one is 1 by root 2 times 1 1 1 minus 1. If you multiply, you should get back the same matrix, that was 2 1 1 2. This is for this matrix only, everything we are doing. So if you multiply this 1 by root 2 1 by root 2, this will become half, and just compute it, and you will look at it, this will look as the half has come out. Okay, and even if you do the inverse calculation here, you will get a half, because the determinant of this will be half. 1 into minus 1 and minus 1, so this will be minus half will be there, so determinant is minus 2. So because of this, the inverse will also have a same effect here. So if you see these two look of the same format, because it is symmetric matrix, it may be different for other, so you will get the same value. Just compute this and compare, you should get this back. I hope this is clear. Okay, so why are we studying this? So Eigen Value Decomposition, it is very, so what is the application? So this is widely used. So the first and foremost thing I have been discussing again, Eigen Value Decomposition will be used for principal component analysis. So I'll discuss this in another video. I'll put the link also in the description. So principal component analysis is another important, which is used for dimensionality reduction in machine learning. So EVD is the concept behind that. The EVD we say for Eigen Value Decomposition. So it is used there. So apart from machine learning also it has application. For example, the Google search ranking, the page ranking algorithm. So that also uses Eigen Value Decomposition. There the importance of a website is decided by the number of other websites which are linking to that website. So the page rank also uses Eigen Value Decomposition. There are other out of computer science, there are other applications in structural engineering while building bridges. So all the bridges will have their some natural frequency. Okay, and those are their eigen values. So if some like wind or some seismic activity acts in the same direction as their natural frequency, so in that direction the increase in the momentum of that force, whatever is given by the wind or some seismic activity, will be amplified a lot because of this eigen value concept, and that may cause the bridge to resonate. There will be some resonance again. The concept of physics, if you remember, there will be resonance if this is coming in the natural frequency direction, okay, the structure's natural frequency. So that will cause resonance and the bridge can break. I hope this is clear, the applications. Okay, so PCA, page rank algo, and then structural engineering for finding natural frequencies. So that will be their eigen values. In which direction, so we'll design the bridges accordingly. In which direction the natural frequency lies, so that I can design that it doesn't lie in the natural path of the wind in that direction, so that it doesn't amplify the vibrations and it will cause resonance. Okay, so these are the applications. So that's all here. So let's do a quick revision. So what did we understand? So in this video was about eigenvalue decomposition. For that we had to understand eigenvalue first, eigenvalue, and for that we understood eigen. Eigen is a German word which means proper or characteristic. In our context it is characteristic. Okay, so it gives me some characteristics about the matrix, a square matrix. So it tells me what is the direction in which, okay, what are the direction of the vectors in which if the transformation by a matrix is applied, there will be no change in the direction, only the magnitude will change. So a matrix does a linear transformation on in vector, right? So it won't change the direction of that vector, only the magnitude will change, and those such vectors for that matrix are the characteristic or eigenvectors, and the magnitude by which it changes, they are eigenvalues. So this is eigenvector, eigenvalue, and based on that, after that we derive the characteristic equation. How to solve that? The determinant of that characteristic equation will give me the value of the lambda or the eigenvectors, because it will give me a degree n polynomial and n lambda n degree, okay, lambda to the power n. So this will have n solutions. So it will give me the n solutions for all the lambdas for this matrix. Okay, and why this was 0? So we computed that a minus lambda I, and this is a vector in some dimension, and now it is becoming 0, means there is some dimension collapse. That's why. So this is non-zero, and multiplication by this matrix. So this matrix must be singular, only then it is causing a dimension collapse, which is causing a 0 here. So this is non-zero. So because of this, we saw that what is the condition for a matrix to be singular, means its determinant should be 0. So we understood that. And then we did some problems, and then we understood the properties of eigenvectors and eigenvalues. So the sum of eigenvalues is the trace of the matrix, product of the eigenvalues is the determinant of the matrix, and then we moved on, saw some values, and then we moved to a concept called diagonalization. Okay, why diagonalization is important? So if we diagonalize a matrix, all operations like taking a power of that matrix, a to the power k, that becomes very easy. The diagonal matrix, if we scale or increase in power, so only the diagonal entries need to be multiplied by that power. Okay, that's why diagonalizing a matrix is good for mathematical applications and other applications also. That is one of the use cases. And then we understood how to diagonalize a matrix. Then we put all the vectors in a vector V, all the eigenvectors and lambda across the diagonal of other, and we saw that is equivalent to like multiplying all the vectors a v1 v2 and getting the lambda 1 v1, this format. We just clubbed them all together and put them in a beautiful matrix format, nothing else. And then finally we got this equation, and we just jumbled it up, okay, just reshuffled stuff, and then we got V inverse AV is equal to lambda, and that is a diagonal matrix which we know because we have that matrix. And then this is here, this shows that this is a diagonalized matrix. Now A has been converted into a diagonalized matrix just by multiplying by the vectors of a matrix of its eigenvectors. The columns are eigenvectors, and then just reshuffle that, and then we can write the same vector as a product of its a matrix of its eigenvectors, a lambda which has all the lambda values and the inverse of that. This is called eigenvalue decomposition. That was the main thing. And then we also saw that if it is symmetric matrix, then the for distinct eigenvalues we will get distinct eigenvectors. For distinct eigenvalues we'll get perpendicular eigenvectors. We proved that also. Here we proved for distinct eigenvalues, for distinct eigenvalues we'll get orthogonal eigenvectors, and we proved that for it is for a symmetric matrix. We did a proof and we used it later again, that since already the vectors that I have got for a symmetric matrix, right, the vectors that I have got, they are already orthogonal to each other. If I just scale them using the by the length, so they'll become orthonormal, and after that for orthogonal, then this matrix V will become orthogonal, and I can use the beautiful property of orthogonal, that is A transpose, where A transpose is equal to A inverse. Where is that? This is the property of orthogonal matrix. A transpose is equal to A inverse. So this inverse calculation is a bit cumbersome, so we replaced, and also it may not be feasible all the time, so we replaced this inverse with a transpose, and we got this matrix. And this has got a name. This is called spectral decomposition, and this is for a symmetric matrix because of the condition that for distinct eigenvalues, eigenvectors would be perpendicular or orthogonal only if the matrix is symmetric. On that condition only we proved that. Okay, so that was your spectral decomposition. And then finally we saw the applications. The most important application is PCA, which we'll discuss next. And then it is also used in page ranking algorithm for Google search, and then also in structural engineering for designing bridges, where we find the natural frequency of the bridges using eigenvalue concept. Okay, I hope this is clear, this helps. Okay, this is very important concept. This is the foundation for understanding principal component analysis and singular value decomposition. So those videos also, I'll put the link in the description. Okay, on that note, let's end this video. Thanks for watching this video. Have a good day and bye for now.